And there's the register file. And it's basically 8 general purpose register. But I write 7 here because the first general purpose register is a hardware 0. And the way I implement it is just to deselect the register file when you are accessing register 0 and add a pull-down register, pull-down resistor to the data bus, to the internal, like CPU internal data bus. Basically, if you are accessing register 0, the resistors are going to pull the bus down. It's going to be 0. That has a lot of uses, but I'm afraid that the resistors might not pull down the bus fast enough that it will be a like frequency or clock rate bottleneck. But I'm not going to bother that because I'm just aiming at like something like 1 megahertz at first and then just go up like slowly and see what the limit is and just swap like components and redo designs to like push that limit further. I'm aiming at something like 10 to 20 megahertz eventually, very eventually. But then going back to the registers, then you can see the times 7 times 2. Why there's this times 2? Basically, the register file is actually duplicated. You can see that the dotted line here basically means that these are A and B register files, and they are not like the backup register file you can find in the Z80. Like the B register file is not a backup of register A that you can like back up in one command and retrieving another command like for fast interrupts. It's not like that. The B register file is a complete duplicate of register file A, and in all operations they should like behave like a single register file. And the reason why I have this B register file is that basically I want to access my operands in one cycle. If I do it using only one register file, I would either use 2 cycles to access the operands one at a time, or option number two is to double pump the register file. Basically, you clock the registers as twice the frequency that all the other things run at. And this is actually a common use technique in microprocessors. Like in the Z80 we discussed before, the ALU itself is double pumped. And it uses a 4-bit ALU to perform 8-bit instruction or 8-bit operations. So it's quite impressive that you can just double pump your ALU like that. And the term double pump is actually used to describe, I think it's Pentium 4 Northwood or Prescott. I don't know, some version of the net burst architecture where Intel basically double pumped their ALU, basically like they just went on a time machine and stealed their own chief engineer's idea from like 1970 whatever, 77 I believe it's, but yeah, and they use this cool term double pumping the the ALU basically you're pumping it with data and data, and then you pump it at double the rate, which is really cool. But I can double pump the register, or I can just run the register at one frequency and divide that frequency by 2 and run the other system, all the other system at the divided frequency. That's another way to think about it. But this will create a very severe, I believe, like frequency bottleneck. Basically the register file will be the bottleneck of every operation, because this thing literally runs at like twice the speed. So therefore it will reach the bottleneck way earlier than all the other systems. So currently the bottleneck is the branch instruction, because I cannot do instruction prefetch if there's a branch miss. So if the current intention is, if there is a branch miss, then insert one no op. If the branch, it's not like it branch hits. If it doesn't branch, then we can continue like one instruction per cycle. And finally, there is a control unit. I'm listing all the instruction that the control unit is in charge of. Right here, jump. I don't know why I just capitalize it like that, because the instruction is not jump. The instruction is JALR, jailer. It sounds like my processor is in jail. It's jailer. But I mean, it is obviously a RISC-V command, and it means basically the same thing as it does in RISC-V. However, there's no jail. JAL command, because there's just not enough space to put all those instructions into 16-bit. And I really want to keep my instruction set simple. So that basically means you have very little headroom when you are trying to do like PC relative things. You need to like use JALR or jailer to retrieve your PC every time and do arithmetic on like the general purpose registers, and then you like jailer again to the PC relative address. It is not actually recommended practice. And basically what I'm thinking about is that you don't do like address independent code and leave the address independency stuff to the memory management unit. It's basically how I do it in the like Z80. Basically, because there's no way you can efficiently do address independent code using Z80 assembly. So I just say screw it and let the memory management unit do it. Yes, there is a memory management. Did I spoil my own video? My own future video? Oh, that's crazy. So, and jump and branch, there are 6 kinds of branch. Like, I don't know, it's the Chinese like figure for 6. So yeah. There's like jump if greater than, jump if lesser than, jump if equal, jump if greater than unsigned, jump if lesser than unsigned, and jump if equal unsigned. Oh no, there's no jump if equal unsigned, because signed and unsigned equals are equal. So yeah. So there are 5 actually. Wait, let me see. Oh my goodness. I'm like doing a live stream now, but I'm not going to edit out anything because nobody is going to watch this video. So yeah, anyway. Oh, there is a branch if not equal command. Why am I so stupid at times? Come on. Because you don't need to compare it like equal, but there's a not equal. So there are 6 conditional jumps, conditional branches, and those are all like inter-register comparisons. You cannot compare a register to an immediate. Why? Because I cannot put all those commands in 16-bit like instruction space. That's the reason. But you can do comparison with 0 because, well, there's a 0 register. So yeah, that's why it is there. The 0 register is basically like, if you are familiar with like Unix or Linux, it's basically both your dev 0 and dev null. It's basically an infinite source of zeros, and it's basically an infinite black hole or trash bin for whatever you don't want. In my current implementation, spoiler alert, the value does get written into the register, but it is never retrieved because when you want to access register 0, the register file will just go like inactive. And there is this syscall command, system call command, or just sys for short. And I have to confess, like, the system call is from Sword Art Online. So I just think like system call is it's somehow just cool for whatever reason. But there is also a break command. It's basically like the interrupt command in x86, or like the break, the 00 in like 6502 assembly. Basically, both of these instructions breaks into the environment. But the syscall is what you use in normal conditions, and break should be for debugging only. Basically, if your program is like a release build, it should not contain any break command, or the break command is only used when there's a dire situation that your program needs to terminate immediately. Basically, you detect like a memory error, or you detect like the integrity of the program itself is like not guaranteed, or like something that is not impossible. It's like something that is impossible just happened. Like, I don't know, if you compare a number and say it's like smaller than something, and then you compare it again and it's greater, or basically things like that. Basically, if you think your program like just was hit by a cosmic ray or is tampered with, you can break. But normally you don't use that. And there is a clever design to it. And all 0 command in RISC-V is a break. It basically, it's an illegal command, and the processor will just breakout. In the Dragonfly, it's a no op. It's not that I think it's more like intuitive that all zero, no op. It's not like that, because it really makes sense if like all zero is a legal command, because all zero is what you get when your memory is cleared. So if you jump to an illegal address, like the illegal instruction like exception will catch that error. And then like, but I know it makes sense, but I just cannot squeeze that instruction into the space and makes all zero a like illegal instruction. I can like force it to be an illegal instruction, basically add some decoding and detect that and cause like a break or a trap or an interrupt or anything you like to call it. But it's like not natively an invalid instruction, because it is basically, I think it's an add or actually a shift with both source registers are 0 and the destination is like the 0 register. Basically, if the destination is the 0 register, it's a no op. But an all 1 instruction is a break, and that is by design. I really want to make all 1 an illegal instruction, and that can be sometimes more important than an all 0 invalid instruction, because when you have like cleared like EEPROM or like FRAM, I don't know about FRAM, but mostly EEPROMs, when they are cleared, they are all 1s, so it's like FFFFFF. So in hats, so that will help. And the last one is LUI. There's no AUIPC command like that in the RISC-V. So again, like PC relative, like long jumping, not a thing. At least not recommended here. So there's only LUI, but you can do LUI and then jailer. Oh my god. And you can do jailer and jump to any absolute instruction, jump to any absolute address, but not like any PC relative address. LUI is just load upper immediate, like it loads an upper immediate like it does in RISC-V. And like in RISC-V, you can do an LUI and an add with a 0 register and an immediate. You can do first add with a 0 register and immediate and LUI. No. What am I talking about here? You can first do an LUI and add the destination, the LUI destination, with an immediate to like load any 16-bit like immediate. And then we comes to the elephant in the house. Basically, in order to squeeze all the instructions into 16-bit, the immediate field is really small. So that affects a few things. First is that all like arithmetic instructions involving an immediate can only use values ranging from -16 to +15. Basically, it's a 5-bit sign like immediate. Like RISC-V, there is no like 0 extending the immediate. Like all the immediates are sign extended. So yeah, that kind of further limits the range, but I think the Berkeley guys must have a reason to abandon that like 0 extended immediate, and actually explicitly saying that they don't find a purpose for 0 extending immediate, like in their documents. So the documents actually says that no, it's just a waste of instruction encoding space, and I really need that encoding space. So yeah, but the greatest effect is the branch instruction. The branch instruction is I format. Oh no, it's B format, like the RISC-V B format. It basically just branch to like 16 instructions before to 15 instructions after. If you cannot do a tight loop, if you are doing a very big loop, not actually a very big loop, just not a tiny loop, basically a loop that is more than 16 or 15 instructions long, you are running out of luck. You need to like choose the opposite condition and make a forward jump and jump over a LUI, L-U-I, and a jailer. Basically a like absolute jump instruction. So if you want to make it address independent, you need to like skip over a jailer, a LUI, add, yes, add to make a AUI PC and another jailer. So not recommended again. So yeah, that's a few like shortcomings of this instruction set, but it used like fixed length instruction encoding. The instruction encoding is relatively efficient because it's 16-bit. It's like the thumb instruction set, or like the RISC-V compressed instruction set, or the Super H that powered the 32X and Sega Saturn and Sega Neptune. Okay, that last one didn't really exist, right? So yeah. Yeah.